Good morning. My name is Andrey Kudryavtsev. I'm SSD solution architect at Intel, working on non-volatile memory products, especially NAND-based SSDs and Optane-based SSDs on the 3D crosspoint memory. So today I'll give you guidance how we see these products through the evolution of our HPC storage, how we work with DDN, and what ideas you can get with DDN to use these products in real products. All right. So I will start with very simple directional, I would say, challenge that we had for years. That since we introduced NAND-based SSDs into the market, we were able to improve the performance of the storage significantly. And that's what today you can see this SFA 14K configurations with NAND-based drives, and that's what we see with other vendors using NAND products and even using local SSDs in your compute servers. The problem that it doesn't solve the challenge of your memory gap, and still memory is significantly faster than your storage performance. So we did a few different product directions that help you to optimize your cluster architecture and node architecture to improve your storage performance and memory performance by introducing basically a full variety of different products. One of them based on Optane technology. Optane technology is Intel name for 3D crosspoint memory, and 3D crosspoint memory is a low latency, very high predictable I/O, media cache line addressable for storage and memory. So we produce SSDs based on 3D crosspoint. Marketing name is Optane. They are available today, already almost 2 years, and we just announced the production of our Optane DC persistent memory. That's a 3D crosspoint memory on a DIMM form factor. So that's something that you put inside your memory slot, close to the DRAM, and it sits on a PCI bus, on a DDR bus, and it communicates to your processor directly. Unlike with storage, typically we do that with PCI Express interface, or in certain cases we do that with SATA SSDs as well. So that's one option how you can close that gap between the latencies and performance of your storage, and between your DRAM performance and NAND SSD performance. There is another improvement that goes to the cost effectiveness of that solution, and this is what we are doing with evolution of the NAND-based technologies and moving through our architecture for NAND-based SSDs based on their TLC components to the QLC. QLC introduces another bit per cell, so that gives your basically higher capacity per component, so up to 1 gigabit per die of NAND. That's a lot of data, and that gives you cost advantages because within the same footprint you can save more data. So basically the QLC is the next evolution of the NAND-based drives optimized for the capacity and being cost effective. And so it's really separate in this area here. And can you see my screen? No, I don't see it. And it's just designed for the needs of a very high capacity and still very high performance. So how would you use that in a classical, I would say, or most typical HPC infrastructure? Of course, there are certain applications which do have a needs for very fast block of scratch. This is not necessarily the case for everyone, but we definitely know that's the case for many, where you have to have local SSDs on your compute node in addition to your parallel file system and shared root directories. And these can be different products. It can be Optane SSDs, can be NAND-based SSDs, can be a SATA drive, but in fact you benefit of having local SSDs. However, it's expensive because you have to populate your SSDs in every compute node. So over the years, many customers decided, okay, why don't we have some pool of I/O nodes, and let's call them I/O node because we have some I/O capabilities. And these nodes have SSDs, these nodes can run job directly, or these nodes can interface to your parallel file system. Example here is a burst buffer solutions. And in case of DDN, again, it's IME class of solutions, where you have a pool of SSDs, rich pool, and you accelerate your access to your storage by doing access to the I/O nodes first. And of course, there is a storage opportunity, how we can improve the storage performance. And usually, there are certain areas inside the storage where you need performance improvements. I'm not speaking about the storage overall, which can be based on hard drives. Sure, why not? It's cheap, it's high capacity. But the first that needs to be improved in the storage is metadata performance. And within the metadata, usually it's a really tough configurations, especially if you create and manage many files, million files at a time. Metadata has to run faster. Metadata is your bottleneck, can be your bottleneck to overall file system. So having some very special products like Intel Optane SSDs inside metadata is the key how you can improve the performance of your parallel file system, not actually changing their full storage completely. However, there are many options how you can make a tiering of that file system and introduce different tiers inside the same parallel file system, like inside the last tree. And this is something that you can actually do with SSDs very cost effectively using QLC-based NAND SSDs and running these SSDs for HPC workloads. Actually, you can tier your storage into high-performance tier, which can be smaller capacity, obviously, and larger capacity, your archive tier or your main home directories. Can be different cases. And of course, there is always a challenge of a memory capacity inside the compute node, which is another topic for discussion. But basically, we solve that challenge through the Optane SSDs. And we introduced a product which is a software product which loads on top of our SSDs and converts these SSDs into a system addressable memory. So your compute node can see the drives as system memory, unlike storage devices. And this is something that you can really utilize in cases where you really need lots of memory inside your compute node. And that's the most transparent of the application because you don't need to make any application changes to use this technology. There is another next level of that technology using what's called Optane DC persistent memory, and that's where we put Optane SSDs onto the DIMM form factor, and then it introduces persistency. So with persistency capabilities of that media, you now don't need to move the data. The data will stay there. Well, no matter what happens with the system restarted or system shut down, you'll get your data back from that type of memory. However, you have to make sure that your application can utilize these capabilities of persistent memory through their APIs or programming modules. So, what makes Optane SSD special for these type of solutions with metadata or with caching? Well, first of all, you're not going to get a prize, you know. You got that already. It's good for you. Alright, so what makes them special? First of all is low latency. Significantly lower latency than NAND-based SSDs gives you predictability on their I/O, for especially very random I/O, where you cannot control what happens with your storage. That's typically not the case for the storage as a storage, that's the case for metadata. And with metadata, you don't know what happens next time when customer creates another million files on your metadata, and that would be really heavy on that side. So that's where really you can benefit of having low latency SSDs as part of that, not actually increasing the cost of your storage because your storage keeps unchanged. Also, this set of products, they have very special endurance capabilities, so they are extremely high endurance. We have products with 60 drives per day, so it's a 60 times you can overwrite the drive during the lifetime of a drive is 5 years, and that gives you capability to basically use it in very tough environment, especially where you have no control of your workload. It can be a write buffer, it can be metadata server, very serious workloads that have to require very high endurance. So here I have an interesting information for you to share that actually came from DDM, and that came from the Lustre team within the DDM under the OneCloud at DDM. And this is our first test of Optane SSDs in storage mode inside basically Lustre OSTs and comparing them to very good NAND-based SSDs. So what you may see here, so there are 4 lines basically. There are 2 tests, reads and write tests. So there's a line for read test, there's a line for write test, and both top lines are performance numbers for Optane SSDs, 4 of them under ZFS configuration, so basically 4 reads and 4 writes. And 2 bottom lines are the same basically workload, the 4 drives on ZFS but NAND-based SSDs. So what you may see here, I'm just not comparing the average performance. Average performance is basically can be different, depends how many drives you have on the platform. So you may have more drives NAND-based technology and get to the same level as you can do with Optane. That's feasible. The main challenge here that with NAND-based SSDs, as you may see here, the performance is not consistent. So there is slight deviation of the performance keeps that happening over the time. And that's the case for every NAND-based SSDs. So why that's happening? The reason is very simple. Every time we're writing to the NAND-based drives, we do lots of background operations to the NAND media. By the architecture of that technology, we have to do erase cycles before doing any writes, and usually you do erase by really big blocks. In order to do erase by big block, you have to read the data first, recombine it, erase, and put it back. So there's overhead that's happening on the NAND media constantly when you do writes, and that affects the write performance. That's why the write performance that you see here in red for NAND-based SSD, it's constantly changing. It keeps in a good level of average, but unfortunately this is not something that you can rely on. Could be certain conditions where workload cannot tolerate that performance deviation. Very similar happens on the reads, because on the reads, read performance is constantly changing when you have some write IOs going on at the same time. And that happens as well when, for instance, you're reading some data from a NAND-based drive, at the same time you're updating timestamp or you're updating their, I don't know, attribute information. And that creates a write onto the drive, and that write always disturbs your reads. This doesn't happen with Optane drives. The reason is very simple, because the media is cache addressable, and it has same performance for reads and for writes. So for you, it doesn't matter what you do actually, reads or writes, you have similar performance budget for both of these operations. And reads in this configuration slightly higher, simply because on the writes, we do ZFS parity configurations. So because we calculate the parity every time you do writes on ZFS, it takes some CPU time, and that's why you see lower writes operations. In general, on SSD you don't see that, but because there is another layer of ZFS, you see that. That's also expected. I think that's it. That's what I wanted to show you today. So thank you for attending. If you want to learn more, welcome to Intel booth. You'll see that technology running in live mode, and you'll see other products of us. Thanks.